稍微等一下哈。Okay, so I'm now connecting to YouTube. All right, we're officially live. Hey guys, it's Grace. Thank you so much for joining me in today's interview of the premiere of Industry Leader Interviews. All right, sorry about that. The connection was a little bit convoluted. So thank you so much for joining me today in today's premiere of the Industry Leader Interviews. So I believe that equity has a much powerful force than that in the real estate business, which should be focused on the value of people and driven by production. And I hope you'll really enjoy today's interview as I hope to kick it off with many more innovations to come to create values and build high equity population that transform the way of property holding. So without further ado, it's my great honor and pleasure to introduce to you today's special guest, Dr. Zhou. Welcome, Dr. Zhou.
Thank you, Grace, and I really appreciate you giving me this opportunity to kind of talk about the science and innovation, how those innovations could benefit people. So thank you. That's my honor.
It's my great pleasure. Dr. Zhou received her Ph.D. in electrical engineering from the University of Arizona, and her specialty is in microwave and optical engineering. And she's currently serving as a senior research scientist at an internal high-tech company. And her working experience includes pioneer work in wireless communication, silicon photonics, digital high-speed I/O, radar technology, and neuromorphic computer. And she's also a senior member of IEEE, the Institute of Electrical and Electronics Engineers, and a guest editor of IEEE Communications magazine. And she's serving as a technical committee member for the IEEE Microwave Symposium, co-chair of International Symposium of Quality Electronics, Neuromorphic Computing, IEEE Electrical Performance Electronics Packaging Systems, and IEEE European Conference of Antenna and Propagation. She holds 14 US and international patents and has published more than 45 journals and conference papers. So in today's interview, Dr. Zhou will be providing knowledge of the invention as to how to deactivate COVID-19. And the invention is currently in the process of filing for patent. So we're very excited about that. And at the end of the interview, we'll have a QA session. So guys, go ahead and type in your questions anytime throughout the interview and we will address them, if not earlier. So Dr. Zhou, can you tell us more about your specialty area in physics?
Okay, so actually I have a wide variety of working experience, and before I came to the United States, I served as a faculty in two of the universities in China. So back then my working experience is more in the mechanical engineering side, and then sensor, like optical photonic sensor. So I started working on microwave engineering since I came to the United States, believe it or not. So when people talking about like autonomous driving, I almost laughed because when I first came to the United States, it was under Caterpillar's fellowship, and my research activity was to enable the autonomous front-end loader, basically trying to remove the human operator from operating the front-end loader in some hazard site. So I did a lot of sensor work, and then like artificial intelligence. So when people talk about AI, I just say, oh God, I did that a long time ago. So anyway, but my specialism mainly focus on the microwave engineering and silicon photonics. So the microwave engineering is basically deal with the waves. So I'm thinking about things like the heat and the sunlight, all that, and wireless communication. So I'm always thinking about, oh, that's just waves. Okay.
So, what is the technology that can deactivate the virus?
Oh, there's a so actually there's some many aspects of that. So actually I prepared a few slides. I just I wanted just to show my slides. Basically in my slides, in one of the slides, I listed all those possible means to deactivate or inactivate the virus. So let me share my screen, so I can show the technology, can be considered. So let me
Sure.
see. I'm trying to find. Where's my slides? Sorry.
So in the middle, there's a green button. You
Yeah,
can.
I know. So actually, I'm trying to locate my slides. Actually, my slides is over here. So on my slides,
Okay.
so I just want to kind of talk about, the COVID-19 virus in Russia. So actually I took this picture from one of the poster in Yale News. So you can see it. This is
You can
it.
go ahead and put on the full screen.
Okay, sure. Let me put into the presentation mode, and then I try to use my pointer. Okay, so you can see this is this is how the virus looks like physically. So you have the this membrane and enclosed um, some gene informations inside this enclosure. Then you have the spike neurons. No, not spike neurons, spike proteins. Sorry, spike proteins. Then this spike proteins serve as like um, I call them antenna because it's basically they try to find a site and attach. That's how they invade our system. So the problem with this is the virus is highly crafty virus. I mean, in the sense they're pretty smart, and what they do is once they get to our body, they just take over the protein production and start replicate themselves and shut down the protein production for our body. And some of the protective proteins won't be able to produce because this monster just take over the factory and start order things around and start organize the meal production. So then so how can we stop the virus from spreading? um and that's the question we want to ask. So the first step is try to destroy this protein. Okay, and
Right.
you can look at this enclosure or membrane. They're just like a fat, so the can melt down. Okay, and you can destroy them from the bio molecule perspective. But based on my background, so I'm not thinking about in that sense. I'm not thinking about in the sense of like a chemical or biochemical or biomolecule level of things. So I'm more thinking about how can we create a device and can destroy the virus, but without some environmental hazard, right? Like you use chemical solving or solvent or whatever, you use a wiper, you always have, the waste. So I want some device I can use and to kill the virus. And then in the meantime, I can reuse it. And so that is a motivation. So again, to answer Grace's questions, let's just go to the next slide. So just look at the virus from the physics perspective. It's quite small. It's look at the individual virus. The diameter is 270 nanometers. It's really really small. So besides it's small, then you need to think about what is a mechanism to really destroy those proteins, right? So there's several means I listed here. That's just my thoughts. It might have more means which wasn't under my radar. So the first one is the mechanical. You just use like a abrasive force. So basically, you have some like you use alcohol or like a paper towel. You scrap them, right?
I see.
Yeah, but this is very small. So
Yeah, it's
when
impossible to do that.
yeah, it's very, very, very hard to see it, so you when the things you use to try to scrap the things so small, it's just really hard to really make it efficient. So the second method would be just a mechanical dissolution. So basically just put a chemical uh, um, solvent there, just try to dissolve the proteins. And the third method would be just use heat, because like I said, you look at the members and the membrane and the spike proteins. They're basically made of carbon, uh, carbon, right? So
Right.
you can use heat to really destroy them. And then the fourth one would be just use electromagnetic waves, just basically trying to have the electromagnetic waves to really again um, change the energy level of the molecule. So let me just give you one example of what this really means. So um, let me just give you a live example. So you go outside, right? So you expose yourself to sun. So the sunlight actually has the contents of the UV light is ultraviolet light. So ultraviolet light has a very small wavelength. The wavelength is about 100 nanometer to 400 nanometer. So that whole spectrum, that 300 nanometer spectrum, is divided into three categories I will talk about later. So basically, when you go outside and you expose yourself to the sun, what's going to happen to your skin? You will
It's
tan.
basically burned. Yeah.
Yes, because the energy level, the energy somehow gets into your skin and they change the molecule. So basically, um, let's just give another example. You cook the food, right? So when you overcook, what happened? It's tend to be brown, and later
Yeah.
on, it's just turn to be black. Then why is black? Because the carbon is black. So basically, you want to just carbonize the whole thing. You just try to break the molecule. So think about you have the like the organic tissues that have a carbon and they have oxide, they have a hydrogen, and so they form like molecule chain, right? So you get rid of some other things, and the molecules basically just um, will dysfunction. That's how we want to just deactivate or inactivate the virus. I will probably stop sharing. Grace, let's just
Okay.
get going.
So
I hope I did not confuse you guys. I try to use a very simple terms. I think science is fun,
yeah.
to not scare
So
people. Yeah.
so so let me ask you this question.
Mm.
Is the deactivated virus, is it still infectious?
No, it's not. Like I said, the most important thing is, you just make you break that protein molecules. Actually, we did some research on so how effective those technology can do. So the technology we're targeting is mainly focused on the waves, right? So we want to either generate the heat through the electromagnetic waves, or we
Mhm.
generated the waves directly. So we just want to destroy the protein molecules, or make it kinds of deactivate. So called deactivate is just look at those those spike proteins, right? They have to have a certain shape, and they have to have like a certain shape to attach to our to our body. So those like receptor sites, when you deform them, and when you deform them, regardless what methods are, and they no longer form attachment. Let me just give you one example. You just go do one experiment. So you have some like you to have two fingers, right? So you want those two fingers are like like locked to each other. See, the finger has to have a certain shape of this gap so you can latch it. So when your hands are basically deformed or somehow get injured, you will no longer form the perfect attachment. See my hand? So you see the gap? So it's no longer form a perfect attachment to really penetrate into our T cell. And by the virus, it has to have a perfect attachment to the receptor on our cell, be able to penetrate and probably, start replicate itself.
I think that's a very good example to show exactly how it works, because like in theory, it's very abstract. So so what you're saying is that the part of the virus that's deactivated is the receptors, correct?
Yeah, so the deactivated, like I say, there's many ways, right? So you number one is just completely burn it, right? So
Right.
that whole thing just tend to be a carbon. So number two would be just deform the site, the receptor sites, so they're not going to form any kind of attachment. Yeah.
I see.
So what yeah, go ahead.
So another question I really want to know, and I also think that a lot of the audience are very curious, is that this technology deactivate the variants that are changing all the time. Like we like little control over it. How does
yeah, so again, like I said, this is not really from the biological biomolecule level. This is really from the physical level. So so you have to remember the variants. What is really vary, right? It's not the membrane of the virus cell. It is not the protein shape. It's the DNA. So that is varying. So let's so remember that that model I showed. I got it from the Yale's news. And so inside that, look at that thing. Basically you can think about it's kind of a softball. Okay, so the softball has those spike neurons that just make, I call them antenna. They try to detect the attaching sites and start communicating, then take over. So, but inside that a softball, that's a DNA, that's gene information of the virus. So when the virus really get into our body and they start, copy the genes and then start reproduce the proteins and wrap around those replicated genes. So the variance is basically talking about the genes, inside that softball changed. But I already burned the whole house. Why do you care about something inside that house? Understand?
I see.
Yeah. So it's this is a mechanical or physical way to destroy it. So basically, yeah. Okay.
Can I understand it as no matter how the DNA changes, using a mechanical or electromagnetic method is more permanent or persistent, no matter how the DNA changes. So basically it kills the variants.
Yeah, right? Yes, basically just, just like I said, you can change anything in your house, but I'm burning your house to the ash. So you have no means to replicate. Yeah, but that's that is basically the beauty of looking at the things from physics level and not from the molecule or, biochemical, or, from the medical perspective, just to say, okay, I just want to destroy this thing physically, period.
I see. That's awesome. That's a very original solution that I've ever heard of in terms of COVID-19.
Uh, so Grace, I have to interrupt you, but actually it's not, so people have been practiced this type of infection in the hospital for years. So let me just give you one example, right? So you guys all know, the ultraviolet light hospital use, and they just basically drive those robots, right? The robots just immediately the UV light and kill the bacteria, kill the virus. But to kill the specific virus as this small, probably the traditional UV light, in the, I call them in the A range of the UV spectrum, would not be efficient.
I see.
So the technology, the thought process, the theory is not new.
I see, yeah. But it really requires like a different approach to
exactly
understand how it works.
So the innovation would be on the implementation sides. So how can you make like a portable device, right? And then you can carry in your pocket, and then you can just take with you, and that can be energy efficient, and can be massively produced at a very low cost.
So another question is that, is this technology safe for people?
The answer is yes or no. So basically the technology we folks just use the wave. So it really depends on how you use the wave. So for instance, we just try to use the wave to generate the heat. So as long as we can control the temperature, and it's relatively safe. So later in my presentation, I will show a table. So people actually did a lot of, we're scientists, we do a lot of study before we think about the solutions viable or not viable. And so from that perspective, it is safe. But if we're trying to use like a short wavelengths, very, very short wavelengths, which matches, the diameter of the virus, so that's actually, in the C range of the UV spectrum. So there's some kind of how to say, there's no clean cut it's safe or not. It really depends on which wavelengths you're using. And so some people just argue to say, okay, if you use the you want to really kill the virus, you have to use something smaller, so that meaning the wavelength has to be small. Just why is that? One time I was talking to my son about this. I just said, the lights or the waves see things. It only matters to them when you have those scattering effects, meaning they're relatively small compared to the wavelengths. So you want to targeting that the virus, with a diameter, spherical shape of diameter, 270 nanometer. You have to make the wave length smaller than that. So so people just argue, said, when you get to that level of the wavelengths, when the release the lights that have a lot of energy, because that was the equation basically showed, the frequency is equal to the delta Eg, which is the band gap energy divided by a constant. So you do the math, you said, okay, the energy basically is the frequency of the signal, which is the wave, time that constant. So smaller the wavelengths, larger the frequency, you get a lot of energy. It could damage your skin or your eye. But there's a lot of study has been carried on and lately, and actually we found in some of the, we call them far, far higher range of the UVC. Um,
Mhm.
they are not really dangerous to humans' eye and the skin. So, but there's a lot of regulation about what you can use in terms of safety. So, in short answer is yes or no.
I believe that you mentioned you are sharing some slides with our
Yes.
audience as well.
What?
Do you have some slides that you can share with our audience?
Yes, I want to share with the audience. So first, I want to just show you the approach we're going after, and some of the the experiment that people already did.
Okay.
I want to just make a statement. The research we carry on in my daily life or with my colleagues, we are basically working on the wireless communication. So we're not expert of in any sense about like a biomolecule. So the information we got in terms of the safety is all based on the the public informations. So let me share my screen. I want to show a table. Um, Let me just put on. And so here is, here's the, the things I talked about. And the first thing we just say, we just think about the heat. So heat is relatively safe in the sense, but you have to think about it. You cannot generate too much of a heat because then you will burn, people's skin, right? So what would be the temperature range you want to target and how long you want to expose to be? um, we need to follow the study from the clinic. So this actually is from this first first reference, and so this reference basically showed, okay, people haven't been considering use the heat to destroy the virus, and you can see they have a virus with different strain, and then you can see it with the same temperature and with the same duration time, and then the log reduction, meaning say after exposed for a certain amount of time at a certain temperature, what is the reduction? So the log reduction, if the log is like a log is a 3, right? The number is 3, meaning it's already half reduction, 50% of a reduction. So you add another one, that's, another 3, that's 75% of a reduction. So the log reduction 7 means just completely, you could consider it's completely killed the virus. So you can see, with the different strains. So for instance, with a temperature set to like 56 Celsius degree, and you just expose for 10 minutes, and the log reduction is 5. So meaning it's already, 50% of the virus gets killed, and more than that, it's almost 70%. That's for the, the strain like a herbal strain, but they have some like a F1, no protein strain, and you need a longer time to kill it. Um, so, so this is the fact. Then there was a lot of study showed, okay, I might not be completely burn it, but I can close the sites, the receptor bonding motify present on the receptor bonding domain of S1, where S1 basically is the protein, the virus protein, begin to close around temperature of 40 Celsius and attends a completely closed conformation at 50 C. So that is the serve as kind of a guideline for us to consider what kinds of a temperature we want to get into if we want to use a thermal solution. But again, the thermal solution, you could have just a traditional way, just like your hair dryer. You know the hair dryer, right? Everyone knows hair dryer. So basically, it have a bunch of coils. You flow the electrical current, and then you have that heat. Basically it's burn power is I square R, and depends on how odd you want to have more power, and you make the R really big, and that gets transferred to be a heat. But that is not the way we want it, because that would make things gigantic, and plus we just want to make pretty efficient. So our proposal is just using again using the electromagnetic waves. So we propose just say you have some kind of source to generate the um, infrared wave. Okay, so infrared wave. So this picture actually shows this is kind of the heater. You can go to Home Depot, buy those heater, and when it's start generating the heat, you can see those glowings. So meaning that the really radiated um, uh, infrared waves. But this is not really efficient. So this is another example of the device. They're using the same series, they're just using the infrared to generate the heat. So our approach is basically we want a small form factor device. We want energy very efficient. So we're trying to so basically, we're trying to make the system work in that sense, and be able to generate the infrared wave very efficiently. And then we want them not just consume a current all the time, meaning they're not powered on. So we are thinking about instead the continuous BIOS. Those devices we're using some kind of impulse modulation, so we could save power. So there's a lot of innovation going on over there. So Grace, I just want to get back to you. I hope I answered your question.
Yes. So you mentioned that this can be made into a device that people carry all the time. So I want to ask, well, where do you see this invention that can be used in our lives, and how do you use it?
So first, our first thought was to make some portable device. It really depends on what you really want to targeting. So like you want to use in the office. So for instance, you are not really constrained by the energy consumption and the size. So this is, you have one set of solution. So it's more in the traditional way I just showed you. But if you want to just make it portable, which meaning you can, put it into your pocket and travel with you. So that is the the device we want to target. So basically, it's a little bit bigger than a book, and that's what we were thinking about. You can carry in your knapsack, right? So you can use it to. So for instance, you go to any place and you can turn on that device. You can desanitize the surface, and then particularly we want people just be able to desanitize their face mask all the time, because the face mask, once you really wear the face mask, if you do not keep it clean all the time, and you're exposed to the viral loads, and you were overloaded by the viral, and then that's not going to protect you. So that is what we intend to use.
So I also think that you mentioned this can be used in like AC system, or it's kind of filter. So can you explain?
Yeah, so this is going back to, so if you just want to use in the filtering system, this is the one is trying to, when you have the AC filtering system, you basically install that, and then you just kind of let the air passing through, and the wave will will penetrate into the virus cell, and deactivate the virus through the wave absorption. And so those one thing I want to point out is um people did quite a bit of study on what kinds of wave see every so every molecule or every kinds of object they have their own transparent window. So usually the transparent window varies with temperature, right? And so we need to find out that window for the virus is opaque, meaning the can fully absorb the energy and the wave. And so that's one thing I want to mention. So to answer your question on Grace, the answer is to use the very short wavelengths, the most likely than in the UVC range of the wave, and then kinds of a shining through the filter. So when the air passing through the filter, it's already exposed to those the very short UV wavelengths, and that carries a lot of energy because I explained uh, previously, the energy is basically is the constant time the frequency, and the frequency is very very large. Okay, so because the wavelength is so small, it's a very large of energy, is very energetic. So once the virus um, is exposed to that UVC light, it's just going to be burned, literally. Yeah.
I see. That's awesome. So,
Yeah.
device, I want to know like what kind of range does it cover? For example, if you use it in a restaurant, with one device, can you cover the entire restaurant or?
No. So if it's a restaurant, or the restaurant, you need multiple device. So
Okay.
our approach is just to say you basically has those devices mounted on robots, and the robots actually, it's not just a single robots. It's a multiple robots, like a former like a robots fleet, and the robots can communicate with each other. Okay, so the kinds of coordinate with each other with wireless communication, and some kind of protocols. So this technology is already, it's already, how to say, it's invented by the company I work. They call them a smart manufacturer. So we basically just want to use the platform they already have, because they have all this communication infrastructure in place. You use Wi-Fi to coordinate everyone, and they already have some sensors. So we just want to mount the device we want to mount it on, to make those robots to move around, to clean the room.
I see.
We even thought about, instead of having the waiters to go clean those contaminated surface, which is a health hazard for them, just file, the robots fleets, just have the robots clean the table and kitchen or a bathroom. And a bathroom is another another sites we really want to have those kind of an instrument. So you just go there, basically you have the robots, it's waiting there, you basically just say go, and the robots just go in to clean up, and then you just go there and activate the robots, and robots clean up, and then you just send you the signal. So you say, meaning the bathroom is already clean, or the some kinds of a segment of the bathroom it's cleaned, will just tell you which one is clean, which one is occupied by people, right? So there's a there's some things going on there. So we're just trying to use a platform and the existing technology called smart factory, and then have mount the device on the robots. Yeah.
So the smart, as I understand, the smart factory infrastructure is already in place. So that makes
Yes.
this device easier to implement.
Yes, actually, it's kind of the device. Actually, it's just the add-ons. You can consider it to be a lot of sensor. So the technology we are trying to protect is how to make this sensor, in a sense, how to make this sensor um, to be efficient, energy efficient, right? And then has less health hazard, right? It's not going to cause any kind of kind of a damage. So even for the for all this for the heat, like a heat sensor, a heat solution use infrared wave, uh, we all considered to have like some kinds of alarming system, like I can use some kinds of device that can just shoot the thermal picture. So it will tell you the hotspot, because sometimes when you generate the heat, right, the heat is not evenly distributed. So some spot could become a hotspot, and once it gets to a certain temperature, it can catch fire. So there's a lot
Yes.
of so it's not
Yes.
just that so you have to uh, because this is the we want to use in the sense of you could have human, like carry, like a portable device, carry with you, and you can use anytime you want, or mount on the robots, right? But regardless of what it is, you do not want to cause any additional health hazard or safety concern. Yeah.
So like if people can carry this device around them, do you use
Mhm.
a battery to use the device or?
Yeah, you use a battery, so you have to charge the battery from time to time. So that is why the power consumption is very important, because you want to save the power, and you want the device lasts longer, in a sense. So the low power is something we must have, and to make this uh, device to be like they don't need to be charged like your electrical cars. You go like 200 miles, and you go charge. And plus, we really do not want to use any very exotic material, like the like electrical cars. The battery use a very exotic mineral. We don't want that. We want to be able to massively produce.
Right.
And energy efficiency is very important.
So you also mentioned that this is not a chemical method to
No, it's a
sterilize.
physical, yeah.
Like disinfectants, cleaners, they have the hazard to the environment. And
Yeah, then they're not good for your body, right? So you just give you one example. So you carry the like a hand sanitizer.
sanitizers.
So you use them for quite a bit of time, then you can feel your skin start getting itching and dry and this sort of thing. And plus it just produce waste.
Right.
Some of the chemicals in those sanitizer, and you inhale, it could cause some kind of problem. We never know from long terms, right? So this see, we want to use the wave, but we do not want to cause any of the radiation hazard. So there's a lot of regulation uh, in that sense. So like I say, this is really not just the uh, pure science. This is like involves the science concept, and then the implementation, which is engineering, and then production, which is industrial engineering. Then you have to follow the government regulation for the safety. Yeah.
So how does it contribute to energy efficiency?
How does you mean how can we make it energy efficient, right?
Yeah, because it doesn't it's energy efficient, and it's also friendly to the environment. So can you explain a little bit about, like, because there's no products like this on the market yet?
And no, not yet, because all these products, and the produced, right, there are many targeting the size like a bus, like a bus, right, like a hospital, a womb, right. So energy is not the concern, because they can just plug into on the powers, power outlets, and power that baby. They just go, right?
Yeah.
But for the portable device, no, you cannot do that. You use a battery. The battery has it has its own power capacity. It has the capacity, cannot draw, cannot provide the very large power, right? So how you do it, there's a many way, like I mentioned, said, so number one, we try to use, like, for instance, for the thermal, we try to use some material actually has a thermal inertia, right? So basically you heat it up, and when you turn it on or turn it off, they have some latency to really drop down the temperature. So we try to make use of that. So we want to, we want to have those, like, we want to be able to use that. So for instance, it depends on what the material is. For the wood surface, right? So you once it's heated up, and you want that cool down, it takes a longer time than you do the same thing with a metal. So you have the thermal conductive material versus thermal non-conductive material, right? So we're trying to figure out, the range of those, we call them latency, meaning you turn off the device, and how long it takes for the surface to really drop down the temperature. So in other words, we're not continuously file the device. We file it, we turn it off, so there's no power consumption, but the temperature keeps. So I don't know. One time I was showing my son an experiment about this concept, this thermal initial concept. So I basically boiled the water, and then I put the eggs, I cracked the eggs and put the eggs into the water. Then I turned off the stove, and then a few minutes later, the egg was cooked. So this basically is using the same principle. So you do not fire all the time. You have some kind of wake up. So that's why we needed the thermal sensor, not just to monitor the hotspot, prevent anything catch fire. In the meantime, you monitor, that surface temperature. So once it goes down like a few degree, probably you really don't care. And then, but if it's dropped down, like, so for instance, you want to close the sides, the receptor sides as one protein sides, right? It requires the temperature to be 50 degree. Maybe it still remain closed until it drops to 40 degree. So you just say, okay, as long as I can keep the temperature for 40 degree for several minutes, I'm okay. I don't need to continue firing. But once the temperature is dropped down to to too low, and then you monitor the time, you say that I do not get enough exposure time, so I file again. So there's another, like, a turn on and turn off time. So basically what we want is we want to have a very quick turn on time.
Right.
Okay. But we want to have a slow turn off time. What that means is, when you turn on the device just can fire it and right away, okay. But when you turn it off, the heat is still still radiating. They're not going away
Effective.
right away. Yes. So how do you make that happen, right? That's another science question. Yeah.
Right. So let me ask you this: what is the longevity of this device? Like, meaning how long can you use it for? How many years? For as long or
This is a really good question, and I really do not have a straight answer for you, because there's a lot of how to say, there's a lot of unknowns here, right? So from the core device, supposedly they're rated with the hours, right? So they're rated with hours, but there's another part of this whole device. So maybe the device is not, it's not the first to fail. Maybe something else is, it went out,
sure.
right? It
So
goes out. So
it's
it's still unknown
processing.
until we have the device, and we call them, we call them the, thermal stress, or the like expedite lifetime testing. We have the data plus the products. Usually they have variations. So it's the same device made by same factory could have a kind of distribution. So until we get to that stage, we really don't know. But what we really targeting is, we want to at least keep the device alive for like 3 years. That's what we were, not on the extreme environment, right? So there was another one. So it's so we were talking about this. Just say, okay, you know what? Maybe we need to install into the car, the
Right.
car, like you go the rental car, and somebody run, and they're just, that person's already infected, but
Yeah.
he doesn't know, she doesn't know. So the whole car is loaded of the viral, the viral load is very high. So say,
Yeah.
you want to put it into the car. So then, my colleague would say, no, not thinking about that right now, because automobile industry has its own, test conditions, meaning this the device has to survive in a temperature range from like a minus 40 Celsius to like 100 Celsius.
Nice.
Then okay, so certainly when we were thinking about device, we're not thinking about that in that extreme condition. So again, answer your question, we do not have a straight answer at this stage, and really depends on the environment we want to use.
So as I understand, there's a lot of questions that are answered today, and it's also still in the process of perfecting. And we really hope to see and use this device like out in the market. Maybe you can go to Home Depot, CVS, or any kind of store,
Yeah, so
find a
yes.
device and use it.
Yeah, that's definitely, the you really want to make make this device really work for people. You have to be massively produced. So like I showed some pictures of, those heat guns, and those uh, heaters. And
Right.
so for the folks that just the stay home, or they just travel with cars, right? So you can go to Home Depot, get those heat guns, okay? And the heat guns are safe to use, and some are just portable, so use batteries. They're pretty heavy in the sense, and you
Not
so
really travel friendly.
yeah, the can travel with you, especially the heat guns. Heat guns
I
can
see.
definitely travel with you. Um, so there was a couple of different variants of the heat guns. So one is just a traditional, we call them long IR heat guns. So those guns that the temperature doesn't go very high, and it usually goes up to 100 CCS. But I think that's basically good enough, right? And then there's another one is the IR based heat guns. It can really go to a very high temperature, can go to like 400 Celsius. But when you have that high temperature, um, you make sure you don't catch fire.
Yeah,
Don't
it's
file them
not really
for
safe.
so long, right? So those tools are sold in by Home Depot. They're just they serve their own designated purpose, but just for your own usage, you want to kill the virus. I think that's adequate. That is adequate. So the device we're targeting basically is in the factory, like can work with the smart factory fleets, and then that's one extreme. We call them landing zone. So another landing zone is something like the size of a book. So it's really really lightweight, energy efficient, and then very safe to use. I don't need a lot of knowledge. So some of the tools, like I mentioned, those tools you have to read the instruction very carefully, not
Right,
skip words to make it work for you and not hurt you, right? So the device we want to provide is just say, I want absolutely no accident,
right,
and anyone can use it, even a kid.
right. So is it safe for people of all ages? That's the
Yeah,
other question that I really
yeah.
know.
So we wanted, so then like we even think about when you're shooting the when you radiate the UV lights, right? So when you radiate the UV lights, so you assume people kind of fall away from you, right? So the energy actually decayed when once reached to the people. So let's just say you're using that, some kids are coming, pop around, and we want to make sure there's no hazard to that kid. So we actually try to incorporate some of the intelligence into the device. It's kind kind of can identify there's a moving target around and how close it is to my device.
So in
So
other words, that it is safe for regardless how old you are.
yeah, it is. That's our goal. See, we want to just we want to just like everybody uses cell phone, right? Regardless, and even the little kid, they
Right.
can play around with your cell phone, and you don't want to. That's a problem for them. It's the same thing for the device we want to provide, especially for the the just household usage. Of course, for the factory and for the restaurant, and like a cleaning the bathroom, that's a different story. But still, we have to follow the government regulation for safety for those device. And the government has a very very restrictive regulations for certain device.
So we really hope to use this kind of device, like you can put it in a pocket, right? Like really small. And
Mm-hmm.
and that's what we're hoping. Like consumers
Yeah.
want something that's portable, that's convenient and easy to use, safe. That's the end goal.
Yeah, exactly. We want, like I said, so um, we want to be able to massively produce. Okay, so massively produce to bring down the cost. We want to energy efficient. We want to hazard free. So it's so the principle, scientific principle is I explained. I hope the audience, and through my explanation, it grasped what is the core physics behind it. But the implementation is very very painstaking to make this happen. So that's the most innovations are. So in terms of innovation, it goes two ways. One is called conceptually innovation, right? So another way is implementation innovation. So this is more on the implementation innovation perspective.
All right. Thank you so much for Dr. Zhou's phenomenal invention that we hope that it can bring an ultimate and complete end to COVID-19. That's been long overdue. It's staying for too long, and we want like forever.
Yeah. So sorry, Grace, to interrupt you. So, because this is actually, regarding this, it's kind of having a pending patent attached to it. So unfortunately, I could not talk about more about some of the details until the patent office they start publishing. So meaning they already did the patent evaluation, and any technology we referred to does not infringe others' patent, and then they can publicize the application. So at that stage, we probably can talk about more exactly what is.
Exactly, and that's what we want to do. And to follow up, we hope to see the patent filing complete, and also this device manufactured, mass produced, so that it can be brought straight to the consumer's hands and they can use it. So
yeah, I certainly hope so.
Yeah, we are very excited to look forward to that happening. So we'll be following up with this technology. Thank you guys so much for tuning in for today's industry leader interview. And thank you, Dr. Zhou, for sharing the knowledge with us with an ocean of knowledge here.
Thank you, Grace. It's just, like I said, I often said when you turn around and you find science. So just turn around, in every corner of your life, there is a science, and science is just, it's amazing. It's so much fun. And thank you so much for having me here and to share my fun story. I hope the folks that are watching this video have a very how to say happy weekend, and stay well and safe, and just think about the virus is a science, and it's nothing scary. Just don't be scared, and there's a way to really overcome it, the damage it does to us. So just don't be scared.
Yeah, we definitely look forward to a safe and healthy environment where everybody can, go back to normal.
Yeah, so I want to make one comment. So the device we invented, we try to make, it's not just targeting one kind of virus. So literally can kill almost every aspect you could imagine the virus. So it's not really, like I say, it's physically destroy the the powerhouse of the virus. So it's not just targeting one, it's targeting many.
And I hope that this interview is the beginning of many other future inventions that you can bring to our audience. So Thank you guys so much for tuning in, and I hope you have a wonderful rest of the weekend. Bye.
Okay, thank you, Grace, and thank everybody watching.